we have discussed about universal active filter, which can be used for a variety of second order filter formulation. Now we are going to convert it into voltage controlled filter, so that the frequency omega naught becomes proportional to a voltage, and then use this filter to be automatically tuned to an incoming frequency. This is called self-tuned filter design. Now how it is done can be explained by understanding first how it is converted into voltage controlled filter and how the multiplier facilitates this feature, and the same multiplier also can be used as a phase detector to tune it properly. Now what is a multiplier? Multiplier is the next important building block after the op amp. It can be used for a variety of communication applications. Like multiplier actually gives you an output which is product of the two inputs Vx and Vy, okay, and a reference voltage Vr. A standard multiplier has Vr as 10 volts, okay, and actual multiplier, okay, has certain non-idealities. It is a part which is independent of the two inputs, that is called offset voltage, and then a part which is proportional to one of the inputs, that is called a feed-through component due to X and feed-through component due to Y. Then the wanted output, okay, K naught into Vx by Vy, where K naught is 1 over Vr. Normally, the extent of dynamic range of the multiplier or precision multiplier is designed to handle as much as the reference voltage, 10 volts in this case, plus 10 volts and minus 10 volts. So this is a 4-quadrant multiplier, okay, which is capable of handling a dynamic range of plus minus 10 volts. Now, how do we use this? First, as a voltage controlled filter, for converting a filter into voltage controlled filter. The integrator of the previous section, which was having a current of Vi by R, going through the capacitor and producing a voltage Vi by R into Sc with a negative sign here. That current is changed, okay, based on the multiplier output. So this Vi is applied here, and this is the control voltage. Now this voltage becomes Vi Vc by Vr according to what we have written there, and therefore the current in this, which was Vi by R, changes to Vi Vc by R into Vr. So we can replace in our previous design omega naught of the filter, which uses the integrator, okay, will have the omega naught change to, from 1 over Rc, it changes to Vc by Vr. So that means the omega naught becomes directly proportional to the control voltage. Q remains as such. That means both integrators have their time constant controlled by Vc, and therefore the omega naught is voltage dependent. That's how we get a voltage control filter. So let us say we have this voltage control filter block, which is getting an input frequency. Our purpose is now, this is, let's say, Vp sine omega Rt. It's a reference frequency that we are having as the input. We want our filter, which has a control voltage, to be tuned exactly to this incoming frequency. Now we are comparing the incoming frequency and the output frequency using this multiplier as the phase detector, right? So what happens here, if this is Vp dash sine omega Rt plus phi, because we have seen that both the magnitude and the phase change as it comes out of the filter. Let us say we have taken the low pass filter output, which we have studied, and the low pass filter gets subjected to a phase shift starting from 0 up to pi, and its phase shift is exactly equal to pi by 2 at frequency omega naught equal to omega r, which is the same as the incoming frequency. So we know that it is exactly tuned to the incoming frequency omega r if this phase shift, okay, phi gets adjusted to pi by 2. And how do we get the information? We know that this output is nothing but Vp dash sine omega rt sine omega rt plus phi divided by dr. So if you now expand this, this is equal to Vp dash by 2Vr, okay, into cos phi minus cos 2 omega rt plus phi. By putting a low pass filter after this, we can get rid of this 2 omega component and get an average which is nothing but proportional to cos phi. And if phi is pi by 2, this average is going to be 0. So the moment we measure 0 average, we know that the filter is having its omega naught exactly tuned to omega r, which is the incoming frequency. So if therefore we compare it with 0 reference and put a comparator and then connect it back, and if this is a negative feedback system, this automatically adjusts the control voltage, okay, such that this voltage is same as this voltage, which is 0. That means every time some input is coming, this gets adjusted to 0, which means all the time, okay, it is getting tuned to the incoming frequency. This is called a self-tuned filter. So if you now apply a square wave here and take the output of the band pass filter, automatically it gets tuned to its fundamental, which gives you a sort of gain of H0 into Q as the gain from the input. That means it's only selecting the fundamental. If the amplitude of the square wave is A, okay, fundamental component is 4A by pi, and that into H0 Q is all the time the output of the band pass filter, irrespective of the incoming frequency. So this becomes a spectrum analyzer, right? If you make it get locked to the third harmonic, you will get the third harmonic amplitude of the square wave. So it can be really used as a spectrum analyzer or as a distortion analyzer, where if you select the output of the notch filter, you will get the percentage amount of distortion present in this periodic waveform, having a fundamental frequency which corresponds to omega naught. So this particular block now is a voltage control filter which is getting automatically tuned to the incoming frequency. Let us try to analyze this as a negative feedback system. So we need here, this particular input is nothing but the quiescent, okay? It has nothing to do with input-output relationship of this. This block is called a voltage control filter. Output is here phase and input is a control voltage. So what we is interest is the sensitivity delta phi by delta Vc, which is called kVcp. This is radians per volts. The dimension of this is radians per volt. So voltage is getting converted to phase, then phase is converted again back to voltage, right? So this particular block, which is nothing but the phase detector, has a sensitivity V delta V average by delta phi its input, which is K phase detector. This volts per radians, right? And this particular block, amplifier block, okay, has delta Vc divided by delta V average, which is nothing but A naught. So the loop gain of this system is going to be nothing but, okay, the delta V average by delta, this thing is going to be sine phi, okay, and therefore is going to be nothing but KVCP KPD This whole thing has to be negative, okay, for negative feedback, okay, and then it should be much greater than 1, like in any feedback systems, okay. Then whatever, this is called a phase follower. This is truly the phase lock loop, because here the frequency remains constant, right? This is meant to get locked to pi by 2 all the time. If you apply a V average which is different, such that V average is, let's say, cos 60, then it will get locked to cos 60, okay, such that V average is cos 60, that means phase is 60 degrees, right? We had chosen 90 only because sensitivity is maximum there, okay. So this can be made to get locked to any phase, and that is why this is called a true phase lock loop, okay, where frequency doesn't change. And that's its application is in self-tuning of filters, and that has become very important in the present day electronics, that most of the control loop function can be done by a digital control, okay, and actual filter can be the analog filter, okay, and therefore we can precisely adjust the frequency to whatever value we want, and later on use the system. So this important tuning scheme, where in most of the integrated circuits, the RNC values themselves are not very accurately known. Okay, there can be a tolerance level of the order of 60% variation from the nominal value. So it is bound to be very helpful in precisely making the filter get tuned exactly to the frequency that we want. So precision tuning is possible in IC filters only by this technique of introducing a control loop for tuning. So this has now become very, very important as far as application is concerned in tuning of filters. So suppose we give as the input to the self-tuned filter a square wave of amplitude A now, and the frequency can be anything, right? Let us say it is FR. It automatically gets tuned to FR. What does it mean? At the output of the bandpass filter, we get the sine wave, which is at the input it is 4A by pi, if A is the square wave, right? 4A by pi, that means more than the amplitude of the square wave by this factor, 4 by pi. And that into H naught into Q is the output that is appears at the bandpass filter. And at the notch filter, we get this exactly subtracted from the input, okay, and so it is going to be H naught into A at the output with waveform which can be easily analyzed. It's nothing but the square wave minus the sine wave, fundamental. So you can get this hatched portion, okay, as the output. You can see the dominance of the third harmonic here, okay, and it is nothing but the square wave minus the fundamental times H naught, okay, and this is very nice to observe. If it is exactly tuned to the incoming frequency, then this peak and this peak will be exactly equal. If you just deviate from this side or that side because of the sudden change in phase, right, either this will go up and this will come down, or this will go up and this will come down. This you can observe in the experiment, right? Only when it is exactly tuned, these two peaks will be exactly at the same point. Okay, so please observe this waveform at the output and enjoy this experiment.